Welcome. There is nowhere to be right now, nothing to solve, nothing to hold on to. Let your breathing slow. Let your shoulders sink into whatever is holding you. Tonight we drift through a quiet question about humans and planets, but you need not follow closely. Just rest and let the words settle over you, like dust settling after a long day. Earth's gravity-shaped human skeletal structure over millions of years. Every curve of your spine, every dense weight-bearing bone, was sculpted by this planet's steady pull. Our ancestors' skeletons thickened and aligned themselves against a force that never wavered. That invisible tether has been with you since before you were born. Human lungs evolved to process a nitrogen-oxygen atmosphere at sea level pressure. The air filling your chest right now carries a precise balance, mostly nitrogen, just enough oxygen. Millions of years of breathing, this exact mixture shaped the branching passages inside you. Change the pressure, change the mix, and the body must labor. Here, tonight, your lungs simply know what to do, drawing this ancient air in without effort. Earth's magnetosphere shields humans from lethal solar radiation. Far above your head, an invisible field bends and deflects the sun's harshest particles. It has done this for billions of years, quietly, without applause. Without it, the solar wind would strip away the very air we depend on. You have never seen this shield, yet it has protected every breath you have ever taken. The ozone layer blocks most ultraviolet radiation from reaching the surface. High above the clouds, a thin veil of gas absorbs what would otherwise burn through skin and cell alike. It is only a few molecules thick, spread wide across the whole sky. Beneath it, life spread across continents, unbothered by the fire pouring down from above. This fragile layer has always been part of what allows rest to feel safe. Human circadian rhythms are tuned to Earth's 24-hour day. Deep inside your brain, a small cluster of cells counts the hours of light and dark. It has been listening to this planet's spin since before written history. That is why your body grows heavy now, sensing the turning of day into night. Even in darkness, some quiet part of you still keeps this ancient rhythm. Earth's water cycle sustains all known biological life. Rain falls, rivers gather, oceans breathe it back into clouds, and the pattern repeats without end. Every living cell you carry depends on this endless circulation. It moved through glaciers, through forests, through unnumbered other bodies before it reached you. Tonight, that same water rests quietly inside you, borrowed for a while. Photosynthesis on Earth produces the oxygen humans breathe. In leaves and in ocean plankton too small to see, sunlight is quietly turned into air. This has been happening for more than 2 billion years, patiently filling the atmosphere breath by breath. You are, in a small way, breathing borrowed sunlight tonight. It arrived here first through green and drifting things, long before it reached you. Human bones lose density in microgravity within weeks. Away from Earth's steady pull, the skeleton begins to release what it no longer needs to carry. Astronauts have measured this loss, month after month, in careful scans. It is a quiet reminder that our bodies were built for weight, not weightlessness. Even now, resting under gravity, your bones are simply doing what they have always done. Earth's atmosphere protects people from micrometeorites. Countless small fragments of rock and ice arrive from space every day, and nearly all of them burn away far above our heads. What might otherwise reach the ground instead becomes a brief streak of light in the night sky. This thin blanket of air has been catching these small arrivals for longer than memory. It asks for nothing in return, only continuing its slow, faithful work. The Van Allen belts trap charged particles around Earth. Two vast, invisible rings circle the planet far above the clouds, quietly holding radiation that might otherwise reach the surface. They were discovered only in the middle of the 20th century, though they had been there all along. Their shape shifts gently with the sun's moods, expanding and settling like slow breathing. Even this, unseen and unfelt, has always been part of what makes rest possible here. Let the breath lengthen now, the exhale a little longer than the breath before it. There is no need to hurry it. Each time air leaves the body, let the shoulders drop a fraction more, the jaw loosen, the hands forget their grip. Somewhere in that long exhale, the mind can loosen too, drifting the way a leaf settles on still water. Human bodies depend on Earth, normal air pressure to keep nitrogen safely dissolved in the blood. Rise too quickly through that pressure, whether from the ocean's depths or the edge of space, and the gas can form bubbles inside the body. This is why divers pause on their way up, and why spacesuits are built with such careful layers. The air around you tonight, pressing evenly on every surface of your skin, is doing quiet, essential work. Beneath every field of wheat and rice lies a hidden world of microorganisms that makes the harvest possible. Billions of bacteria and fungi move through the soil, breaking down matter and offering nutrients back to roots. This unseen partnership feeds nearly all of humanity, season after season. Farmers have always depended on this world without needing to see it, trusting the ground the way one trusts an old friend. Human eyes were shaped by the particular light of this star we orbit. Across long stretches of evolution, our vision tuned itself to the colors the sun casts down through Earth's atmosphere. This is why greens and blues feel so natural to us, and why sunsets stir something familiar in the chest. Elsewhere, under a different star, human eyes might have learned to see an entirely different sky. Earth tilts on its axis, and from that tilt, the seasons are born. This small slant, unnoticed in daily life, changes how sunlight falls across the year. Ancient farmers learned to read it long before they understood why it happened, planting by the lengthening and shortening of days. Entire calendars, festivals, and rhythms of rest grew from that quiet tilt in the planet beneath our feet. Gravity, pressing gently downward, keeps fluids from pooling in ways that blur human vision. On Earth, blood and other fluids settle low in the body, exactly as they have for all of human history. Away from that pull, fluids drift upward instead, pressing on the eyes and sometimes changing how astronauts see. It is a small, strange reminder that even sight depends on weight. Across Earth's forests, deserts, and reefs, an immense variety of genes waits inside every seed and every species. This biodiversity gives food crops the resilience to survive drought, disease, and shifting weather. A single wild relative of wheat, growing unnoticed on a hillside, might carry the trait that saves a future harvest. The planet's variety is, in a sense, a kind of insurance no laboratory has yet replaced. Over hundreds of thousands of years, human immune systems learned the microbial language of this planet. Bacteria, viruses, and fungi shaped our defenses long before we understood what defenses were. This shared history is why human bodies recognize so much of Earth's microscopic life, responding calmly instead of with alarm. It is a long, old conversation carried quietly inside every person. Deep below the crust, plate tectonics slowly recycle the nutrients that ecosystems depend on. Vast plates drift and collide over millions of years, drawing minerals up from the depths and returning old material to the mantle below. This slow churning has kept Earth's chemistry in balance since long before life left the oceans. It is a process too slow to feel, yet essential enough to sustain everything living above it. The Moon, faithful across billions of years, pulls at Earth's oceans and steadies its climate. Its gravity draws the tides in and out, a rhythm as old as the seas themselves. Without that steady pull, some researchers note, Earth's axis might wobble more freely, and its seasons could grow far less predictable. The Moon has, in its own silent way, helped make a stable world possible for us to rest upon. Among all the worlds astronomers have studied, Earth remains the only planet known to host a civilization spanning its entire surface. Cities, satellites, and cables now stretch across every continent, tied together by light and signal. No other planet yet shows such reach, such coordinated reshaping of a world. It is worth noticing how singular this moment truly is, resting on a planet still humming with human activity. Let your body grow heavier now, one part at a time. Feel your feet settle first, pressing down into the mattress like stones finding the bottom of a still pond. Let that heaviness climb slowly upward, through your legs, your hips, your chest, each part sinking a little further. Your shoulders loosen and drop. Your head rests fully supported. There is nowhere for this weight to go but down, and down is exactly where it belongs tonight. In 1961, a young pilot named Yuri Gagarin became the first human to leave Earth's atmosphere and circle the planet from space. His flight lasted only 108 minutes, yet it changed how humanity understood its own boundaries. From orbit, he described Earth as blue, beautiful, and strangely small. It was the first time a person saw the whole planet at once, held gently against the dark. Since the year 2000, the International Space Station has never been without people aboard. Crews rotate every few months, but the lights never go dark. The systems never fully rest. Generation after generation of astronauts has passed through its narrow corridors, keeping watch over experiments and equipment far above the clouds. It has become, in effect, humanity's longest unbroken address beyond Earth. Every day, astronauts aboard the International Space Station spend 2 hours exercising just to keep their bones from thinning. Without gravity pulling against their frames, bone density can fall away faster than in any illness on Earth. Treadmills strapped with bungee cords, resistance machines, and stationary bikes stand in for the pull their bodies once knew. It is a strange kind of homesickness written into muscle and skeleton. Skylab, launched by the United States in 1973, became the country's first true home in orbit. It was built partly from a repurposed rocket stage, a workshop stitched together from leftover parts of the Apollo program. 3 crews lived aboard it, testing how long the human body could endure weightlessness. Its legacy quietly shaped every space station built after it. In 2011, the Space Shuttle program came to a close after 30 years of carrying astronauts and cargo into orbit. Its final landing marked the end of an era, built on reusable spacecraft shaped like winged gliders. For years afterward, American astronauts relied on other nations' rockets simply to reach space. The shuttle's legacy remains etched into the way engineers still imagine reusable flight. SpaceX, a private company founded by entrepreneur Elon Musk, became in 2020 the first private company to carry humans into orbit. Its Crew Dragon capsule docked with the International Space Station, marking a shift from government-only spaceflight toward a broader commercial era. What once required entire nations now sometimes rests in the hands of a single company. The sky, it turned out, had room for more than governments alone. Between 1969 and 1972, Apollo astronauts carried back roughly 382 kilograms of lunar rock and soil. These samples, sealed carefully in vacuum containers, still teach scientists about the moon's ancient volcanic past. Some remain untouched in storage even now, saved for instruments not yet invented. A handful of dust, carried across 250,000 miles, still holds secrets waiting patiently to be read. For over a year at a stretch, astronauts have lived aboard the International Space Station without once returning to Earth. Such long missions let scientists study how the human body adapts and sometimes struggles across many months of weightlessness. Muscles thin, fluids shift, and time itself begins to feel different without a sunrise to mark the day. Yet still, people return home, carrying what they learned back down to the world that shaped them. Aboard the space station, Nothing drinkable goes to waste. Systems capture moisture from the air and process astronaut waste, including urine, filtering it again into water clean enough to drink. Engineers designed this closed loop because carrying water from Earth costs enormous fuel. What once seemed unthinkable on the ground becomes ordinary in orbit. Up there, everything usable is kept, cycled, and returned. Astronauts have grown lettuce, radishes, and even zinnias inside small growth chambers aboard the station. Roots spread outward in every direction, since gravity offers no single path to follow. Light-emitting panels stand in for the sun, tuned to wavelengths leaves prefer. Crews have eaten some of this harvest fresh, a small taste of Earth grown far away from it. Green life, it turns out, adapts more readily than expected to weightlessness. Somewhere beyond these words, a low hum rises and fades. A fan, a furnace, the far-off murmur of traffic settling into night. Let it arrive without needing to mean anything. Let it pass without needing to be followed. Your shoulders may slacken a little more with each faint wave of sound. There is only this, breath in, the hum receding, breath out, and the dim room widening around you. Every 90 minutes, the station completes a full circle around Earth. In a single day, its crew watches 16 sunrises and 16 sunsets streak past the windows. Continents slide by in minutes, oceans arriving and receding like breath. Time loses its old shape up there, unmoored from any single sunrise to anchor it. Yet the crew still keeps a schedule, choosing when night and day begin. Lead behaves differently once weightlessness removes gravity's constant pull. Without it working to draw fluid toward the legs, blood shifts toward the chest and head, and the heart itself grows slightly smaller over months in orbit. Vessels stiffen in ways doctors continue to study closely. Blood pressure and rhythm both change subtly the longer a mission stretches on. Coming home again asks the heart to relearn old work. NASA once studied identical twins to separate the effects of space from the effects of genetics. One brother, astronaut Scott Kelly, spent nearly a year aboard the station, while his twin, Mark, remained on Earth. Researchers compared their genes, immune markers, and cognition afterward, looking for what spaceflight alone had changed. Small shifts appeared in gene expression, in gut bacteria, in the length of certain chromosome caps. Most differences faded again once Scott returned home. Scott Kelly lived aboard the International Space Station for 340 consecutive days, one of the longest single missions in American spaceflight history. He watched the seasons change on Earth from a distance no window could shrink. His muscles thinned, his height briefly increased as his spine stretched, and his sense of balance wavered on return. Yet he adapted, day by day, to a life without solid ground beneath him. His mission remains a lasting record of endurance. Small rodents travel to orbit as some of humanity's most patient research partners. Mice and rats live inside specially built habitats aboard the station, letting scientists study bone loss, muscle wasting, and immune changes across generations impossible to test safely in humans. Their shorter lifespans let researchers observe effects that would take decades to appear in people. Careful, ethical review shapes every such experiment. Their small lives extend, in modest ways, what is known about living beyond Earth. A specialized printer aboard the station once produced tools and parts using nothing but heated plastic filament, layer upon layer, in weightlessness. Engineers wanted to know whether printing worked the same without gravity pulling each layer into place. It did, opening a door toward manufacturing repair parts in orbit instead of waiting months for a supply rocket. A wrench built entirely in space became a small symbol of self-reliance beyond Earth. The tool itself now rests in a museum below. Each year, astronauts aboard the station carry out hundreds of experiments spanning biology, physics, materials science, and medicine. Investigations range from growing protein crystals to testing new alloys to observing flames that burn in perfect spheres without gravity's pull. Universities and space agencies from dozens of countries send their questions upward, riding along with cargo ships. The station has become less a single laboratory than a shared address for curiosity. Its orbit carries the questions of many nations at once. Electrolysis splits water into oxygen and hydrogen, and this simple reaction keeps the station's air breathable. Electric current passes through stored water, freeing oxygen molecules for the crew to breathe. The hydrogen byproduct is vented or recycled into other systems. This closed loop means astronauts depend less on oxygen shipped from Earth. A tank of water becomes, quite literally, a tank of air. NASA's Artemis program aims to return humans to the Moon decades after the last footprints were left there. New spacecraft, new landers, and a growing web of international partners now aim toward the lunar South Pole. Artemis intends not just a visit, but a lasting presence, with habitats and rovers planned for extended stays. Its early missions have already circled the Moon, testing systems for crews to follow. Each step retraces a path once walked, then extends it further. China operates its own space station, called Tiangong, quietly circling Earth in its own orbit. Built module by module across several missions, it now hosts rotating crews for long-duration research. Its laboratories study materials, biology, and the effects of extended spaceflight, much like other orbiting outposts before it. Tiangong represents a second continuous human presence above the planet, independent of any other nation's station. Two separate homes now drift above the same blue world. Let warmth begin at your feet, spreading upward the way morning light climbs a wall. Feel it settle into your ankles, then rise slowly through your calves, loosening what the day left tight. Let it reach your chest, spreading wide like something poured and left to rest. Let it move into your shoulders, down through your arms, into fingers curled and heavy. There is only this warmth, traveling through you, asking nothing else of you tonight. Private companies now design their own space stations, imagining orbit as a place for business as much as science. Startups propose modules for research, tourism, and manufacturing, hoping to fill the gap left as older stations age toward retirement. Some plan inflatable habitats that expand once launched, saving space inside a rocket's fairing. Investors and space agencies alike watch these projects, uncertain which will reach orbit first. Orbit, once government territory, is slowly becoming shared ground. Starship rises from its launch stand, built to fly again and again without being discarded. Every part, from booster to upper stage, is designed for return and reuse, landing upright rather than falling into the ocean. This full reusability could lower the cost of reaching orbit dramatically, changing how much cargo and how many people might travel beyond Earth. Engineers still test and refine each flight, learning from both successes and setbacks. A reusable rocket treats space travel less like a single journey, more like a route flown again and again. Blue Origin is building landers meant to carry astronauts down to the lunar surface for NASA's Artemis missions. Its design draws on decades of rocket experience, aiming for a vehicle sturdy enough for repeated trips between orbit and ground. The lander would meet astronauts in lunar orbit, carrying them the final stretch to the surface and back again. Multiple companies now compete to solve the same problem, each proposing a different path down. The Moon, once reached by a single program, now draws several hopeful engineers toward it. Lunar regolith, the fine gray dust covering the Moon's surface, could one day become the material for walls and roads. Engineers study ways to heat, bind, or Dimensionally print this dust into solid structures, avoiding the cost of hauling every brick from Earth. Some proposals melt it directly with concentrated sunlight, fusing loose grains into something rigid enough to build upon. Using what is already there turns a barren surface into a quarry. A future lunar outpost might rise from the ground it stands on. Inside certain craters near the moon's poles, sunlight never reaches the floor, and there, water ice waits in permanent shadow. These pockets of cold have likely held frozen water for billions of years, undisturbed by warmth or wind. Spacecraft carrying sensitive instruments have detected its signature hiding in these frozen basins. If harvested, this ice could supply drinking water, breathable oxygen, or even fuel for future missions. A single crater's shadow may hold resources for lives not yet lived there. Mars's atmosphere is thin, far less than 1% as dense as Earth's, and it offers little shield against radiation from space. Without a strong magnetic field or thick air, cosmic rays and solar particles reach the surface largely unblocked. Any future colonists would need shelter beyond a simple dome or tent to stay safe over long stays. The same thin air that once seemed a mild inconvenience turns out to be a serious design challenge. Mars, in this sense, offers less protection than the world it might one day host. Mars habitat designs often push living quarters below the surface, letting soil and rock absorb radiation that no roof could fully stop. Engineers imagine chambers carved into cliffs or covered under mounds of packed regolith. Some concepts reuse lava tubes, natural tunnels left by ancient volcanic flows, as ready-made shelter. Living underground trades a view of the sky for a longer, safer life. On Mars, safety may mean learning to dwell in darkness by choice. Bringing every drop of rocket fuel from Earth to Mars would make return trips nearly impossible, so engineers propose making fuel on-site instead. This approach, called in situ resource utilization, would draw carbon dioxide from the thin Martian air and hydrogen from water ice, combining them into propellant. A small chemical plant could sit beside a landing pad, quietly manufacturing what a ship needs to fly home. The idea turns Mars itself into a fuel depot. Explorers would no longer need to carry their way back with them. NASA's Perseverance rover carries an experiment called MOXIE, built to pull oxygen straight from the carbon dioxide that fills most of Mars's atmosphere. Over repeated tests, the small device has produced breathable oxygen in tiny but measurable amounts. Scaling this process up could one day supply astronauts with air, or provide oxidizer for rocket engines. Success on a rover the size of a car hints at what a larger version might accomplish. A single instrument's quiet hum may foreshadow how future colonists breathe. A journey to Mars and back would expose astronauts to radiation levels that exceed current career limits set for spaceflight. Outside Earth's magnetic shield, cosmic rays and solar particles accumulate steadily across the months-long transit. Even with careful shielding, the dose received on a single round trip could approach or surpass what an astronaut is normally allowed to absorb in a lifetime. This risk remains one of the hardest problems still unresolved in Mars mission planning. The distance itself, more than the destination, may be the greater hazard. Somewhere above a dim horizon, fog begins to gather, thin and slow, drifting without any hurry to arrive. It moves the way a held breath finally lets go, spreading outward until edges disappear. There is no need to follow it, no task waiting on the other side. Let your shoulders sink a little further into whatever holds you. The fog keeps drifting, and so gradually, do you. SpaceX has stated its long-term goal is a self-sustaining city on Mars, one that could survive and grow without constant resupply from Earth. This vision includes fuel production, food cultivation, and manufacturing all happening locally, independent of any single shipment. Reaching that point would require thousands of successful flights and decades of steady effort. The company frames it less as a single mission and more as an ongoing migration. Whether such independence is achievable remains an open question still being tested launch by launch. Lunar Gateway is a planned outpost designed to orbit the Moon rather than sit upon it, serving as a stopping point for astronauts heading deeper into space. Crews could dock there to transfer between spacecraft, resupply, or rest before continuing toward the surface below. Its position outside Earth's immediate neighborhood makes it a useful proving ground for systems meant for longer journeys. Engineers see it as a stepping stone rather than a final destination. The Moon, in this plan, becomes a waypoint on a much longer road. Private companies have proposed mining helium-3 from the Moon's surface, a rare isotope embedded there by billions of years of solar wind exposure. On Earth, this material is scarce, but lunar soil may hold enough to matter for future fusion research. Extracting it would mean processing enormous volumes of regolith, since concentrations remain thin even where it exists. No commercial operation has yet proven the economics work at scale. Still, the Moon's dust holds a resource Earth simply never accumulated in the same way. Spinning a spacecraft could recreate something like gravity, using rotation to press occupants gently outward against a curved floor. Engineers have studied this idea since the earliest days of spaceflight, imagining habitats shaped like wheels or long cylinders, turning steadily through space. The faster or larger the structure spins, the more convincingly it mimics the pull felt on a planet's surface. No crewed vehicle has yet tested this at full scale, though the physics behind it is well understood. Motion itself might one day stand in for a world. In the 1970s, physicist Gerard O'Neill proposed enormous cylindrical habitats that could house thousands of people entirely apart from any planet. His designs imagined rotating structures large enough to hold farmland, rivers, and open sky painted onto curved ceilings. O'Neill argued that space, not just Earth, could become a place people actually lived rather than merely visited. His sketches, drawn decades before such construction was possible, still shape how engineers imagine off-world living today. A physicist's blueprint became one of the earliest visions of a planet-free future. Inside an O'Neill cylinder, the spin itself would take the place of gravity, pressing everyone outward against the inner shell as the whole structure turns. Standing at the axis, a person would feel almost weightless, while walking toward the rim would slowly restore a familiar heaviness to their steps. The size of the cylinder determines how gentle or noticeable that spin feels underfoot. Long, slow rotation avoids the dizziness that faster, smaller spins might cause. A turning shell, in this design, becomes a stand-in for the pull of an entire world. The Stanford torus takes a different shape than O'Neill's long cylinders, forming a wheel that spins around a central hub. Designers imagined it holding several thousand residents inside a ring, roughly a mile across, connected to solar panels and a docking hub by spokes. Sunlight would be reflected inward by angled mirrors, warming farmland and homes arranged along the torus's inner curve. The hub at the center, spinning far more slowly, would offer a place to dock ships without the outer ring's stronger simulated gravity. A wheel turning in silence became one more sketch of a life apart from any planet. Far out in the asteroid belt, a metallic body named Psyche has drawn attention for what it might contain. Its surface reflects light in ways that suggest a composition rich in iron and nickel, materials common in Earth's core, but rarely exposed like this. Some estimates place its total metal content far beyond anything mined across human history. A NASA mission is now traveling toward it, hoping to learn whether Psyche truly is a fragment of a shattered planetary core. A single asteroid, out past Mars, may hold metal enough to matter for centuries. Beyond iron and nickel, Certain asteroids are thought to carry platinum, palladium, and other rare metals in concentrations that dwarf what remains accessible on Earth. These platinum group metals matter for electronics, clean energy technology, and countless industrial processes here at home. Mining them from space would avoid the ecological disruption that terrestrial extraction often causes on Earth's surface. No such operation exists yet, and the engineering challenges remain considerable. Still, the belt above us may one day supply what our own crust cannot easily give. In 2022, a spacecraft called DART deliberately collided with a small asteroid moon named Dimorphos, testing whether such an impact could measurably change its orbit. The collision shortened Dimorphos's orbital period around its larger companion by more than half an hour, a shift scientists could confirm through careful observation. It marked the first time humanity had intentionally altered the path of a celestial body. The mission wasn't aimed at mining or habitation, but at planetary defense, should a future asteroid threaten Earth. A small nudge, delivered on purpose, showed that our reach now extends to redirecting rocks in space. Let your jaw loosen now, just slightly, the way it does in the last moments before sleep. There is no need to hold your mouth closed or your brow steady. Let your eyelids rest their full weight down, heavier than they've felt all day. Behind them, notice the dark isn't empty, it's soft, shifting, undemanding. Let your face become still the way a lake stills after the last ripple fades. Nothing there is asking anything of you. Scattered across the asteroid belt lies more raw material than most people imagine. Enough rock and metal, in theory, to construct habitats larger than every city on Earth combined. The belt's total mass remains far smaller than Earth's own, but spread across so many bodies, it offers abundant building blocks for orbital structures. Engineers studying these numbers have suggested that a fraction of the belt's material could house populations many times the size of Earth's current one. None of this construction has begun. The belt simply waits, holding possibilities no one has yet claimed. A cable stretching from Earth's surface into orbit sounds impossible, yet the idea of a space elevator has persisted for over a century. The concept relies on a tether anchored to the ground and extended far beyond geostationary orbit, held taut by the pull of a counterweight in space. Cargo could climb this tether using mechanical grip rather than rocket fuel, cutting launch costs dramatically. No material known today is strong enough to build such a cable at Earth scale. Still, the vision persists as a quieter alternative to fire and thrust. Above the clouds, vast solar collectors have been proposed to gather sunlight, uninterrupted by weather or nightfall. These satellites would convert that light into microwaves or lasers, beaming the energy down to receivers on Earth or directly to habitats already in orbit. Because they orbit continuously in sunlight, they could generate power far more consistently than ground-based panels ever manage. The idea dates back decades, though the infrastructure to build such satellites at scale doesn't yet exist. Sunlight, gathered where it never fades, might one day power lives on more than one world. Certain points in space allow a small object to sit still relative to two larger bodies, held in balance by their combined gravity. These Lagrange points, named for the mathematician who first described them, occur at specific spots near the Earth-Moon or Earth-Sun system. A habitat placed at one of these points would need little fuel to stay in position, drifting gently within a gravitational pocket rather than orbiting actively. Several such points exist, each offering a different vantage and stability. A structure floating there would belong to no planet, yet remain steady all the same. A location called L5, trailing the Moon in its orbit, has long stood out as a favored site for large-scale colonies. Positioned in a stable pocket of gravity, structures there would need minimal correction to hold their place across decades. Early proponents imagined thousands of cylinders and spheres clustered in that region, drawing sunlight uninterrupted by any planetary shadow. The distance from Earth remains close enough for supply and communication. A whole neighborhood of habitats, none of them resting on solid ground. Different creatures thrive under different pulls of gravity, and rotating habitats could be tuned to match. A ring spinning faster near its rim might offer Earth-like weight, while an inner chamber, spinning slower, could hold a lighter pull suited to another purpose. Livestock, plants, or even future human generations, bred for lower gravity, might each find a floor built just for them. The habitat becomes a layered world, not one gravity, but several, nested inside a single turning frame. Beneath the Arizona Desert, a sealed glass structure once tried to answer whether people could live entirely apart from Earth's open systems. Biosphere 2 enclosed forests, wetlands, and farmland under airtight domes, testing whether a small world could sustain itself with nothing crossing its walls. Volunteers lived inside for extended stretches, growing their own food and breathing air recycled by their own miniature ecosystem. The experiment revealed how delicate a self-contained biosphere truly is. Even a few acres of enclosed nature proved far harder to balance than anyone expected. Partway through the mission, the air inside Biosphere 2 grew thinner than anyone had planned. Oxygen levels dropped steadily, eventually falling low enough that outside air had to be pumped in to keep the crew safe. Investigators later traced much of the loss to concrete inside the structure, which had quietly absorbed oxygen as it cured, reacting with carbon in ways no one had accounted for. A closed world, it turned out, could lose its breath to its own walls. The lesson shaped every closed system design that followed. Tanks of algae, lit from within, can quietly turn stale air back into something breathable. Given light and carbon dioxide, these cultures release oxygen as a byproduct of their own growth, much as forests do on a far larger scale. Compact and fast-growing, algae bioreactors could sit inside a habitat's walls, cycling air continuously without soil or sunlight from outside. A spacecraft's atmosphere might one day be refreshed not by machinery alone, but by living green water humming with photosynthesis. Roots suspended in mist or nutrient-rich water use a fraction of the liquid that soil-based farming demands. Hydroponic systems bathe roots directly in dissolved nutrients, while aeroponic setups suspend them in air, misting them at intervals. Neither method needs soil, and both recycle nearly every drop of water they use. In a sealed habitat, where water cannot simply fall as rain and replenish itself, this efficiency becomes essential rather than optional. Let your breath find its own unhurried rhythm now, in and out, without needing to be arranged. Notice the small pause at the top of the breath, and the longer, looser fall at the bottom as the air leaves you. Each exhale can travel a little further than the one before it, spilling out like a slow tide retreating from shore. There is no correct depth, no correct pace, only this, breath following breath, each one a little longer on its way out. Let the next one go even further than the last. Grown in vats rather than fields, mycoprotein cultures can supply usable protein without a single seed planted in soil. Fungal strains, fed on simple sugars, multiply into dense fibrous mats that mimic the texture of meat. No sunlight, no acreage, no weather required, only a controlled tank and a steady feedstock. In a closed habitat where every surface matters, this kind of farming could feed people without ever touching a plow. Reworking a plant's own genetic code could make it thrive somewhere no seed ever evolved to grow. Synthetic biology allows researchers to trim a crop's need for nutrients, shorten its growing cycle, or strengthen its tolerance for recycled water and filtered light. Such engineered plants could complete their whole life cycle within a sealed loop, drawing only from what the habitat itself provides. A garden built not by nature's trial and error, but by careful redesign. Around the hull of a deep space habitat, engineers have proposed lining the walls themselves with water. Held in panels or thick tanks, this water would absorb and scatter incoming cosmic particles before they ever reach a living body inside. Water carries hydrogen, one of the more effective materials for slowing radiation, and it serves double duty as a stored resource for drinking or growing food. A wall that shields and sustains at once, holding back the sky while quietly waiting to be used. A magnetic field, generated around a spacecraft's hull, could theoretically bend incoming cosmic particles away before they ever reach the crew. Charged radiation follows curved paths inside a magnetic field, much as it does near Earth's own protective shell. Building such a field strong enough, without drawing impossible amounts of power, remains a difficult engineering puzzle. Physics laboratories continue testing smaller versions, hoping to shrink the concept down to something a ship could actually carry. Metal and minerals drawn from a captured asteroid could be fed directly into machines that print entire habitat frames. Raw material, crushed and refined in orbit, would never need to leave a gravity well or cross the vast distance from Earth. Layer by layer, a printer could raise walls, supports, and chambers from what was once just floating rock. Building this way turns a lifeless asteroid into the bones of a future home. Fleets of small robots, launched years ahead of any crew, could raise the walls of a habitat long before a single person arrives. Each machine, simple and tireless, would repeat its task without rest, without complaint, without needing air to breathe. Together, their combined motion could complete tunnels, seal joints, and wire power systems across a structure far larger than any one machine could manage alone. By the time humans finally step aboard, the hardest labor would already be finished. Splitting atoms inside a compact reactor can heat propellant to far higher speeds than ordinary chemical engines allow. Nuclear thermal propulsion trades the slow burn of rocket fuel for a denser, longer-lasting source of thrust. A journey once measured in many months could, in theory, shrink down toward weeks. Shorter transit means less radiation absorbed along the way, and less strain carried by the body during the crossing. Fusion propulsion, still confined to laboratories and equations, promises a kind of speed no chemical rocket has ever reached. Fusing hydrogen the way stars do could release enormous energy from a small amount of fuel, pushing a craft far faster than anything flown today. No working fusion engine has yet left the ground, and the physics of containing that reaction remains only partly solved. If it ever succeeds, distances between worlds might shrink from years down to mere months. Certain bodies appear to withstand radiation better than others, and identifying that difference could shape who someday travels furthest. Genetic markers linked to stronger cellular repair might one day help select astronauts naturally better suited to the harshness of deep space. Screening would not build resistance from nothing, only recognize traits that already exist in some genomes. Such selection raises quiet ethical questions that space agencies have only begun to consider. Growing new life without a womb of flesh has moved from fiction into cautious laboratory research. Artificial wombs, tested so far only in early animal studies, aim to nurture a developing organism inside a controlled fluid-filled chamber. For a habitat far from Earth, such technology could one day offer a path to reproduction where traditional pregnancy carries added risk from radiation and microgravity. The research remains early, delicate, and far from any application beyond the laboratory. Feel the weight of your own body now, settling further into whatever holds it. Start with your feet and let them grow heavy, as though the mattress had risen slightly to meet them. Let that heaviness climb into your calves, then your knees, then the long muscles of your thighs, each one giving up its hold. Your hips sink next, then your lower back, pressing down with unhurried weight. Feel your shoulders drop, Your arms grow full and still, your hands loosening finger by finger. Let your head rest heavier than before, cradled, unmoving, complete. Bacteria living inside the human gut could be reshaped to work harder in a sealed environment far from Earth's varied diet. Microbiome engineering might introduce strains better able to extract nutrients from recycled food or unusual protein sources grown in tanks. A well-tuned internal ecosystem could ease digestion, reduce waste, and keep a traveler healthier across years spent inside a closed habitat. The human body, it turns out, carries its own small colony that space travel might one day redesign. Plastic waste, instead of accumulating uselessly aboard a habitat, could be melted down and fed back into a printer's nozzle. Recycled polymers, ground into fine pellets, become raw feedstock for building new tools, panels, or replacement parts. Nothing discarded needs to stay discarded, since a closed habitat has nowhere else to send its waste. What once seemed like trash becomes, quite simply, tomorrow's material. Crystals grown in orbit have revealed properties Earth's gravity cannot allow. Without convection currents pulling atoms into uneven layers, crystals formed aboard orbiting laboratories often grow with fewer defects and more uniform structure. Samples returned from these experiments have shown improved clarity, strength, and electrical behavior compared to their terrestrial counterparts. Freed from settling and turbulence, molecules arrange themselves with the precision gravity on Earth tends to disturb. Protein molecules crystallize more cleanly once gravity stops pulling them out of alignment. On Earth, sedimentation and convection distort the delicate lattice a protein needs to form for study. In microgravity, these forces fall away, allowing larger, more ordered crystals to take shape over days of drifting stillness. Scientists studying disease have used these clearer structures to better understand how certain molecules behave, work that could shape future medicine grown far from any planet. A single strand of glass drawn far from Earth could carry light farther than any cable made below. Fiber optics manufactured in orbit avoid the gravity-driven flaws that creep into glass as it cools and hardens on a planet's surface. Without those imperfections, light signals could travel with less loss and greater clarity across long distances. Engineers see this as one small proof that some materials simply behave better once Earth's pull is removed. A Dyson swarm would gather a substantial share of a star's entire output of energy. Instead of one solid shell, thousands of independent collectors would orbit a star at varying distances, each harvesting sunlight and beaming the power onward. Together, they could capture a portion of stellar output that no planet-bound civilization could ever hope to use. The scale of such a structure dwarfs anything built by human hands so far. Freeman Dyson, writing in 1960, described a civilization that might surround its star with structures to capture its light. He proposed that any advanced society, hungry for energy, would eventually build outward rather than remain confined to a single world. His idea, now known by his name, imagined countless orbiting collectors absorbing starlight that would otherwise scatter uselessly into space. The concept still shapes how physicists imagine humanity's distant future. Trillions of inhabitants, by rough calculation, could one day live within a completed Dyson swarm. Each collector platform, sized like a small world in surface area, could support its own habitat, gardens, and gathering spaces. Multiplied across thousands of such structures, the combined living space would vastly exceed anything a single planet could offer. It is a strange kind of abundance, built not from land but from light itself. Matryoshka brains describe a nested set of computing shells built layer upon layer around a star. The innermost shell absorbs starlight directly for power, while each outer shell captures the waste heat radiated by the shell before it. Together they form a vast computational structure, using nearly all of a star's output to think, calculate, and store unimaginable amounts of information. The concept remains entirely theoretical, a thought experiment in extreme efficiency. A branch of speculative engineering proposes taking apart whole planets to supply material for orbital construction. Rather than mining a world's surface piece by piece, entire bodies could be broken down entirely, their rock and metal lifted into orbit for building. The appeal lies in scale. A disassembled planet offers far more usable material than anything ever extracted from beneath a crust. It remains an idea confined to papers and speculation, not practice. Somewhere beyond the walls, a low hum rises and fades, the kind of sound a building makes when everything else has gone still. It might be wind finding an edge to move against, or a house settling into itself for the night. You do not need to know which. Let it come, hold for a moment, and pass on without asking anything of you. Each time it fades, let your breath fade a little with it, slower than before. Disassembling a planet like Mercury could provide raw material on a scale almost impossible to picture. Mercury holds a dense metallic core beneath a thin rocky crust, offering iron, nickel, and other elements in vast quantity. Breaking it apart, piece by piece, could supply enough material to construct orbital habitats numbering in the thousands. No such project has ever been attempted, but the numbers alone hint at how much a single planet actually contains. Orbital habitats could offer more livable surface area than any single planet ever provided. A world's usable land is limited to the fraction of its curved shell that isn't ocean, ice, or mountain. Rotating structures in orbit could stack layer upon layer of open ground, floor after floor catching artificial daylight. The total livable space could dwarf entire continents. No planet, however wide, was ever built with such deliberate efficiency. Rotating habitats could be scaled to house millions without needing a planetary surface at all. Engineers picture wheels and cylinders large enough to hold entire cities, spinning gently to hold people against their inner walls. Farmland, rivers, and neighborhoods could all exist within a single vessel drifting through open space. Growth would no longer depend on discovering new continents. It would depend only on building another structure alongside the last. Space-based agriculture could bypass weather-related crop failures entirely. Storms, droughts, and frosts have shaped harvests since farming began. But a sealed habitat answers to no sky. Light, temperature, and rainfall could all be set by design rather than left to chance. Crops would ripen on schedule, season after season, untouched by any storm outside the walls. Food security would become an engineering problem rather than a gamble with the atmosphere. Off-world manufacturing could operate without atmospheric corrosion concerns. On Earth, oxygen, moisture, and salt slowly wear down metal, machinery, and structures over years of exposure. In the vacuum beyond a planet's air, that quiet decay has nothing to act upon. Materials built in orbit could remain untouched by rust for far longer stretches of time. Entire industries might shift skyward simply to escape the corrosion that shortens the life of things built below. Zero-gravity manufacturing enables near-perfect spherical ball bearings. On a planet's surface, gravity pulls molten metal downward as it cools, leaving tiny imperfections in shape. Without that pull, a droplet of metal floating freely forms into a nearly flawless sphere on its own. Factories in orbit have already produced bearings rounder than any made on the ground. It is a small, precise wonder tucked inside a much larger story. Space habitats could maintain any chosen day length, independent of a planet's rotation. Earth's spin locks its inhabitants to 24 hours, whether that rhythm suits them or not. A rotating structure answers to no such spin. Its lighting cycles could be set to whatever length its builders prefer. A colony might choose a shorter day for work or a longer one for rest. Time itself would become a design decision rather than an inherited fact. Certain proposals suggest cloud cities floating in the upper atmosphere of Venus. It sounds unlikely for a planet known for crushing pressure and scorching heat at its surface. But high above that surface, conditions shift into something almost gentle by comparison. Balloon-like structures, buoyant in the thick air, could drift there indefinitely. The idea has circulated in aerospace circles for years, more sketch than blueprint, but not without merit. Venus's upper atmosphere holds pressure and temperature, much like Earth's near an altitude of 50 kilometers. Far below, the surface bakes hot enough to melt lead under crushing weight, but drift upward through the clouds, and the numbers ease into something almost familiar. A structure floating at that height would feel, in pressure and warmth, something close to a mild day on Earth. The hostile planet, seen from above, turns strangely hospitable. Free-floating stations could migrate between star systems as generational ships, carrying entire populations across distances no single lifetime could cross. Unlike a planet bound to one star, a self-sufficient habitat answers to no orbit but its own chosen path. It could drift outward, decade after decade, sustaining crops, air, and children born who never see a planetary sky. The destination would matter less than the vessel's ability to sustain itself indefinitely. A home, in that sense, could simply keep moving. Let warmth begin somewhere small, maybe at the center of your chest, and let it spread outward from there. Feel it move into your shoulders first, loosening what the day left tightened. Let it reach down through your arms, into your hands, until your fingers feel heavy and warm against whatever they're resting on. Let it pool in your stomach, then drift lower, into your hips, your knees, the soles of your feet. Wherever this warmth travels, let that part of you rest completely, and let the next breath carry it further still. A generation ship bound for another star might take centuries to arrive, long enough that no one aboard at departure would live to see its ending. Children would be born mid-voyage, grow old, and pass their duties to the next crew. The ship itself would become their entire known world, its corridors as familiar as any street on Earth once was. Arrival would belong to descendants of the ones who first left home. Proxima Centauri b circles the nearest star system beyond our own, just over 4 light-years from Earth. That distance sounds small on a cosmic map, yet light itself needs over 4 years to cross it. A radio signal sent today would reach that world only after your future children had already grown. Even our fastest current spacecraft would need tens of thousands of years to arrive. Breakthrough Starshot aims to send tiny light-sail probes toward another star system at roughly a fifth of the speed of light. Powerful ground-based lasers would push against thin reflective sails no heavier than a few grams. At that speed, the journey to Proxima Centauri could take only decades rather than millennia. The idea remains largely theoretical, but the mathematics behind it already checks out. Traveling between stars would expose a spacecraft to particles moving at nearly the speed of light, striking hull and body alike. At such velocities, even a single hydrogen atom carries enough energy to damage living tissue or delicate equipment. Shielding against this kind of relativistic bombardment remains one of interstellar travel's hardest unsolved problems. Thick water walls, magnetic fields, or dense hull layers have all been proposed as partial answers. As a traveler's speed approaches a significant fraction of light itself, time no longer passes at the same rate for them as for those left behind. A journey that feels like a handful of years to the crew could span decades back on Earth. Einstein's equations describe this precisely, and particle accelerators confirm it daily in miniature. Aboard a starship, the clocks and the calendars would quietly disagree. Certain futurists imagine a future where human consciousness could be copied into a digital substrate, freeing thought from a body entirely. In that vision, Memory and personality would exist as patterns of information rather than flesh. Whether such a copy would truly be the same person, or merely a faithful echo, remains an open and unresolved question. The idea still lives mostly in speculation rather than working technology. If a mind could run inside a digital system, its subjective experience of time might no longer match the physical world outside it. A single afternoon in real time could feel, to an uploaded mind, like years of lived experience. Researchers exploring this idea point to how processing speed, not biology, would set the pace of thought. Whether such acceleration is truly possible remains far beyond current technology. Cryonic preservation research explores whether biological processes might be paused indefinitely, holding a body in careful suspension until conditions allow revival. Cells are cooled to extremely low temperatures, slowing decay to something close to a standstill. No method yet exists to safely reverse the process for a whole human being. Still, the underlying question, whether life can wait, continues to draw careful patient study. Engineers have theorized synthetic bodies built to withstand vacuum exposure directly, without the fragile chemistry of living tissue. Such a body might tolerate radiation, temperature extremes, and pressure differences that would end human life within seconds. Material science has not yet produced anything close to this, but the concept persists in serious speculative writing. A traveler built this way could step outside a ship as easily as opening a door. Certain theorists propose that humanity's distant descendants might drift away from biology altogether, becoming something closer to post-biological existence. In this framing, the body would be optional, and the mind's continuity would matter more than its material form. No planet, no atmosphere, no gravity well would remain strictly necessary to sustain such a being. It is only a proposal, resting far out at the edge of what anyone can currently know. Think of a single candle in a dark room, its flame drawing thinner and thinner until only a curl of smoke remains, rising and then disappearing into the air above it. Nothing asks you to follow it. Your breath can slow the way that flame does, unhurried, without effort, fading into stillness. Let your body rest here, in that last quiet moment before the smoke is gone. Nanotechnology could theoretically repair radiation damage at the cellular level. Tiny machines, smaller than a living cell, might one day patrol the body, finding broken strands of genetic material and stitching them back into order. Engineers researching this describe it as a maintenance crew working at a scale invisible to the eye. The idea remains largely theoretical, but it points toward bodies that could heal faster than radiation can harm them. Self-replicating machines could build habitats faster than human labor alone. A single machine capable of copying itself could, in principle, multiply into thousands, each one gathering material and assembling structure without rest. Engineers studying automation describe this as compounding growth, doubling again and again until a habitat rises from what began as a single unit. No human hands would need to lift a single beam. Von Neumann probes are theoretical self-replicating interstellar explorers. Named for the mathematician who first described the underlying logic, such a probe would travel to a distant system, use local material to build copies of itself, and send those copies onward. In principle, one probe could seed an entire galaxy over enough time. No such probe has ever been built, but the mathematics behind the idea remains sound. Artificial intelligence could manage life support systems without human oversight. A system watching oxygen levels, temperature, and water recycling could react in fractions of a second, faster than any person could notice a problem. Engineers designing future habitats describe this as a quiet background presence, always attentive, never distracted. It would not need sleep, and it would not need to be told twice. Genetic engineering could adapt future humans to permanent microgravity. Traits affecting bone density, muscle regulation, and fluid balance might be adjusted so a body no longer weakens without gravity's pull. Researchers exploring this speak carefully, aware that such changes touch the deepest parts of what a body is. It remains an open question whether humanity would choose to change itself this way or simply build gravity instead. Gill-like implants have been proposed for closed atmosphere efficiency. Certain researchers imagine a device that could extract oxygen directly from water or recycled air, reducing the strain on a habitat's breathing systems. The concept borrows loosely from the way fish draw oxygen from water, adapted for engineered use. It remains speculative, resting more in early designs and sketches than in any working device. Radiation-resistant genes from tardigrades have been studied for human application. These small, hardy creatures can survive extreme radiation doses that would be lethal to almost any other form of life, protecting their genetic material through unique proteins. Biologists have already inserted fragments of these genes into human cells in laboratory settings, observing modest gains in radiation tolerance. Whether this could ever scale to a whole living person remains unresolved. Hibernation technology has been proposed for long-duration space travel. A traveler slowed into a deep, torpor-like state might age less, eat less, and endure years of transit with barely any memory of passing time. Some scientists studying this draw comparisons to hibernating bears, whose bodies slow dramatically without harm. No method yet exists to induce this safely in a human being, but laboratory interest continues. Brown fat activation research could reduce metabolic needs during hibernation. Unlike ordinary fat, brown fat generates heat by burning energy quickly, and certain animals rely on it to survive long, cold winters in a slowed state. Physiologists studying human brown fat wonder whether activating it deliberately might help lower the body's overall demands during extended stillness. The research is early, but it offers a biological thread worth following. Suspended animation was tested in pigs to study reduced metabolic states. Researchers cooled the animals' bodies and slowed their vital functions, then observed how well normal activity resumed afterward. The trials aimed to understand whether a living body could pause its urgent processes without lasting harm. Early results showed partial success, hinting that such techniques might one day extend safely to longer journeys. The work remains bounded by caution and incomplete understanding of what stillness truly costs a body. Let your jaw loosen, just a little more than it already has. There is no need to hold any expression at all. Feel the small muscles around your eyes give up their grip, one by one, like something unclenching after a long day. Behind your closed lids, the dark is wide and unbothered by anything. Let your face become as still as a pond, with no wind reaching it, and let sleep find you there. Humanity could become a fully spacefaring species without a homeworld. Certain theorists imagine descendants who never touch soil, who are born and raised entirely within engineered habitats drifting through the dark. Their sense of home would not be a place fixed beneath their feet, but a structure carried with them, generation after generation. This possibility remains distant and speculative, yet it reframes what belonging to a planet has always meant. A Kardashev Type II civilization would harness the full energy output of its star. This would mean capturing not a fraction of sunlight, as Earth does now, but nearly all of it, using structures vast enough to enclose the star's light entirely. Such a civilization could power endless habitats, industries, and machines without depending on any single world. It remains a theoretical marker, one rung on a ladder no civilization has yet climbed. Civilizations are ranked by energy consumption on the Kardashev scale. A physicist named Nikolai Kardashev proposed the idea in 1964, sorting advanced societies by how much power they command. A Type 1 civilization uses the energy available on its home planet. Beyond that lie stars, then galaxies, each step representing an almost unimaginable leap in scale. The scale offers less a prediction than a way of measuring how far a civilization's reach might one day extend. A Kardashev Type 3 civilization would harness energy across an entire galaxy. Such a society would draw power not from one sun, but from countless stars spread across hundreds of thousands of light years. Its structures, if they existed, would dwarf anything built by earlier stages, weaving light and energy through entire spiral arms. No evidence of such a civilization has ever been found, and it remains, for now, a boundary of imagination rather than observation. Using black holes as energy sources for advanced civilizations has been proposed by certain physicists. A black hole slowly loses mass through a faint radiation, first described by Stephen Hawking, and in theory, an engineered structure could capture this trickle of energy across immense stretches of time. Other proposals imagine dropping matter into a black hole to release energy through gravitational stress before it falls in. The idea remains purely theoretical, resting on physics far beyond any current engineering. Dyson swarms could theoretically be built incrementally, starting with small satellites. Rather than constructing one impossible megastructure all at once, engineers might launch modest collectors first, adding more over decades or centuries as resources allow. Each new panel would capture a little more starlight, slowly reshaping how much energy a civilization has to draw upon. The approach turns an overwhelming idea into something closer to a patient, ongoing project passed between generations. Self-sufficient orbital habitats could outlast the habitability of any single planet. A world's atmosphere may thin, its climate may shift beyond recovery, or its star may simply age past the point of sustaining life. A habitat built to recycle its own air, water, and food carries none of those planetary risks with it. It could drift through changing centuries largely untouched by whatever happens to the surface below, carrying its small enclosed world intact. Stars eventually exhaust their fuel and can no longer support planetary life. Deep within every star, hydrogen is slowly converted into helium, a process that powers its light for billions of years before eventually slowing. As the fuel runs low, the star's structure begins to shift, and the gentle balance that once warmed nearby worlds falls away. Every planet's story is, in this sense, tied to the story of its sun, and every sun's story eventually ends. 5 billion years from now, the sun will swell into a red giant, its outer layers reaching outward past the orbit of Earth. The change will unfold across ages too long for any single mind to witness, yet the outcome is written into the physics of ordinary stars. Mercury and Venus would likely be consumed. Earth's fate remains less certain, but its oceans would boil away long before the swelling arrives. Civilizations built around orbiting habitats would not need to face a dying star at all. Long before a sun begins its final expansion, an orbital population could simply relocate its structures toward a younger star elsewhere in the galaxy. No planet would need saving. No evacuation of the surface would be required. The habitats themselves would carry the only home that mattered, drifting onward while the old star faded behind them. Let your breath find its own unhurried rhythm now, in through the nose, out a little longer each time. Notice how the exhale seems to carry something loose and heavy out of the chest with it. There is no need to time it, no need to count. Just let each breath arrive a little slower than the one before, drifting you further down, further in, toward rest. Certain theorists propose that a habitat need not rely on any star to keep functioning. Stored energy, drawn from radioactive decay or vast reserves of chemical fuel, could in principle sustain systems for centuries without a single ray of sunlight. Such a structure would carry its own private sun sealed inside its walls. It would owe nothing to the sky above it, only to the fuel packed carefully within. Fusion, if ever mastered at habitat scale, could power a structure with no star in sight at all. Hydrogen collected from gas clouds or hauled from distant reserves would fuse quietly inside a reactor core, releasing the same kind of energy that lights every star in the sky. A habitat running on fusion would carry its own miniature star sealed at its center. Distance from any sun would become simply irrelevant. Out among the stars drift worlds with no star of their own, cast loose long ago from whatever system once held them. These rogue planets carry no sunlight, only the internal warmth left over from their formation. Deep beneath frozen surfaces, that ancient heat may keep liquid water in hidden layers for billions of years. A planet, it turns out, does not need a sun to hold on to warmth. Rogue planets and free-floating habitats together open a strange kind of frontier, one without a single star anywhere nearby. Proposals imagine colonies burrowing into a rogue world's internal heat, or building sealed structures that simply travel between such worlds like stepping stones. Neither would depend on starlight for anything. The galaxy's dark spaces, once thought empty, might hold room enough for entire quiet civilizations. Far beyond any star's fading, cosmology describes an ending vaster than any single sun burning out. Across unimaginable spans of time, the heat death of the universe would see matter thin, temperatures fall, and even the faintest sources of energy exhausted. It stands as the deepest challenge any civilization could ever face. No habitat, however clever, escapes the question of what happens when the universe itself runs low. Facing that far horizon, certain physicists propose drawing power from the vacuum of space itself. Empty space is not perfectly empty. Quantum theory describes a faint, restless energy humming through it everywhere. Whether that energy could ever be extracted and used remains deeply uncertain, resting on physics not yet understood. Still, it stands as one of the only theoretical answers to an ending so distant it dwarfs every other concern. Long before any of this, Freeman Dyson's own vision already pointed past the stars themselves. His famous swarm was never meant as a final home, only a stage. He imagined civilizations eventually outgrowing even their captured starlight, moving onward into deeper space as their needs and abilities changed. The star, in his thinking, was simply where the journey began, not where it was ever meant to end. Descendants of humanity in this last speculative reach appear as fully digital beings, no longer tied to any planet at all. Minds once carried by flesh and bone are imagined instead as patterns of information, running on substrates built far from any world. A shift like this, were it ever to happen, would close the long chain of biological dependence altogether. Nothing about rock, air, or soil would remain essential to who they had become. Post-biological civilizations, freed from flesh and its fragile limits, could, in theory, persist beyond the lifespan of any single star. Once biology no longer anchors existence, information patterns could be copied, moved, and preserved across vast stretches of time. A star's death, in this view, would no longer mark an ending but only a transition, carried onward elsewhere. Existence itself would stretch further than any sun could ever burn. The idea of a fully planet-independent humanity marks the far edge of this long trajectory, from a species once entirely bound to Earth's gravity and air, toward one that could someday ask nothing of any world at all. Every fact along this journey traced the same slow unfolding, dependence loosening, one small step after another, across generations beyond counting. Tonight, none of that distance matters. Your breath still rises and falls beneath a familiar sky, held safely by the planet that made you. Rest now, beneath that old and steady gravity. Good night.